the most common and classic methods for the feasibility problem is the projection-based methods. Here we mean the orthogonal projections. Two well-known is the methods are the sequential projection method and the simultaneous projection methods. The difference is how we will use the projection, the orders. Sequential means one by one, and the simultaneous is at the same time. And no matter what kind of method we use here, we are based on the orthogonal projection, which is defined by the distance function, the minimum of the distance function. As long as the site CI is closed and convex, this optimization problem has a unique solution. You can always find the unique projection with any point, no matter it's inside or outside of the site. Why we use projections? Because as long as we use projections, we can get closer and closer, at least not further than the intersections. This comes from the firmly non-expansiveness of the projections. And also the convergence proof can also comes from this property of the projections. Okay, and also if we assume some standard error bound, and we can get the linear convergence rate of the sequential and both the sequential and simultaneous projection method. There is a very interesting paper from 2008, which says how good the projection method for the feasibility problem from Nicholas. Actually, in this paper, the authors had some doubt about whether the projections is efficient. But I want to say, anyway, it's a very interesting paper. The author discussed the methods for the feasibility problem with the linear inequalities and the box constraints. He discussed the simultaneous projection method and also sequential projection method and the interior point method. He found that the projections method is not very efficient, but I think it is almost more than 15 years ago. But now I think maybe we can answer this question in another way because of the appearance of the circumcenter. Okay, so the circumcenter first proposed to accelerate the Douglas-Hartford method. Here I want to say something about the Douglas-Hartford. Actually, Douglas-Hartford was first proposed for solving the heat equation, the boundary problem for the heat equation in 1950s, and later by Lyon and Messier, they introduced the Douglas-Hartford method for the finding the 0 point of maximum monotone operators in 1970s. Actually, Douglas-Hartford is a very general framework for many problems, but also for the feasibility problem, it is the DRM is available. The Douglas-Hartford is available, but it can only get the linear rate. The Douglas-Hartford works in this way. For example, we have a point xk and a closed set A and a closed convex set B. We want to find a point in the intersection. So from this xk, we do the first reflection. And then from here, we do the second reflection. Then we have 3 points, RAXK, RBRAXK, and XK. Douglas-Hartford takes the midpoint of xk and the second reflection as the next iteration. So we can see here xk plus 1 is closer to the intersection compared with xk. But the CRM, the circumcenter reflection, means we need to calculate the circumcenter. That is, we calculate the circumcenter of these 3 points. So obviously it is better because we use the information of all these 3 points, and theoretically we can prove that the circumcenter reflection method converges and also has better rate than the Douglas-Hartford. So in this sense, It is a kind of acceleration for the Douglas Hartford. Okay. So it works in this way. Here is the scheme of the CRM. We have set A and B, and we also have X, and the first reflection and second reflection. Then we calculate the circumcenter of this 3 point as the next iteration. And here RA is also is a reflection defined by the projection, and RB is the same. Okay, so this is a picture shows how does the CRM works. We have a point xk here. We do the reflection, and then we do the sequential reflection. We get the second reflection here. So we calculate the circumcenter of this xk, RAXK, and RBRAXK. Then we get the next point, xk plus 1. Here we can see we use this circumcenter for two hyperplanes, so it converges. Why I say it here we use two hyperplanes? Because the CRMs has some problem with the general case. For example, if here A and B are both general convex side, it will not converge. It has some drawbacks of the general case of convex feasibility problem, even with two convex sides. So as long if we want to use the CRM to solve the M set problem, feasibility problem, we need to use the product space, which means if we want to find a point in the intersection of M site, it is equivalent to find a point Z, both face D, belongs to the both face W and both face U, where W is defined by the product of C1 to Cm. So this W, the product site belongs to the product space R n times M, and U is a diagonal, it's a diagonal and also a fan subspace. So as long as we want to, if we want to solve the general feasibility problem, we can solve the problem in the product space. In this case, W is a convex general site, but U is very special, has a structure here. It's a diagonal space. In this sense, CRM can will converge, but at the same time, it brings a problem because the dimension of the space will increase very fast as long as the dimension of the problem increase. Here is a counterexample of what I said before. If we just use the CRM for two general sites, for example, we have an initial point here, and we do somehow the circumcenter, and we get the first iterations here. You can see it gets further than the previous one. So the picture here, the picture on the right side is obvious. You can see the iteration diverge. So this is a drawback of the CRM. When I say CRM, it means the first version of our method, of the circumcenter method. Okay, so to overcome the first the CRM, which means we need to use the product space. Here we introduce Roger and other co-authors, Roger, Luis Rafael, Junior, and Professor Alfredo, they introduced a new version of CRM, which is called the centralized circumcenter reflection method, which is formulated in this way. Let me just introduce a bit here. We divided it into two parts. First is this part, T-map and T-SPM. T-map means it is the operator. It is the operator of the alternating projection operator. T-map means if we have a point D, we just do the projection to A and then projection to B. It's the alternate. You can say it's alternating for two sides or sequential projection. Okay, the second is T-SPM. It's the simultaneous projection operator. if you have a point Z, you do the TSPM. You just calculate the mean of the projections to each side. So first is this part. We do the T map first. We do the TSPM sequentially. Then we get a point. We call it centralized point. So after we do this part, T map, TSPM, with respect to Z, then we get a centralized point. After we get this centralized point, we will do this circumcenter. But we need to be a little attention here. This circumcenter is a little different from the previous one. The previous one, we call it sequential circumcenter. Here, we call it the simultaneous circumcenter. The simultaneous circumcenter means we do the reflections at the same time, not sequentially as it in the CRM or in Douglas-Ashford. There we do the there we can see here. Yeah, here we do the reflection simultaneously. First RAX, then RBRAX. But here we can see we do the simultaneously the circumcenter. So in one word, the circumcenter reflection method is the centralized process and simultaneous circumcenter. Okay, so yeah, I will also introduce a little bit about the centralized point. When we say a point at Z is centralized with respect to A and B, it means this inner product is less than or equals to 0. It means we can see the picture left, right. The angle between Z and the projection, the two reflections, this angle is greater than or equals to 90 degrees. And here we can see this point. This point is not centralized with respect to X and Y, because we can see the angles here is obviously less than 90 degrees. So here I said this process, T map and TSPM, is the centralized process. As long as you give a point ZK, no matter it's centralized or no, after this process, these two operators, you can get a point which is centralized with respect to A and B, like the point here, not this point anymore. Okay, so this is the introduction of the CCRM. But the problem, we have a question here. In that paper, the paper CCRM has been proposed. Roger and other co-authors just solved the problem with two sets of feasibility problem. But here we want to do something more. We want to solve the M-set convex feasibility problem. So the key point here is we have many sites. We need to decide which sites should be used first or then, because in each iteration, we can only use two sites at the same time. Because here we can see the operators here are defined with only two sites A and B. Maybe you can use C1, C2, or C2, C3 here, but definitely you cannot use all the sites at the same time. Maybe possible, but in this sense, it is not. Okay, so the key point is the order of the site. We need to decide the order of the site which will be used in the iteration. So we define LK and RK, this pair, where LK and RK is number from 1 to M. M is the number of the site, and then we apply these orders to apply these pairs to the operators. Then we can define the CCRM to M-set feasibility problem in this way. We have a point ZK and we have operator T. T is the same as before, but with respect to say RK and say LK. And the LK RK is a kind of order. Here we call it control sequence because it controls the order of the site. Different kind of control sequence will give very different performance of the algorithms. Here we will introduce three kind of very popular control sequence. The first is almost cyclic, which means with a kind of generation of the cyclic, you can say if this positive integral Q equals to the number of set M, it is just the cyclics 1, 2, 2, 3, and M1s. It's a very classic one. And the second is most violated constraints in distance variant. Imagine you have many sites. Some are close and some are far away. It is very efficient if you just use the farthest one as the first one. You project to the farthest one, which will get much closer into the intersection. So the most violated constraints means before we do the iteration, we need to calculate the distance from the current point to each site, to C1 to Cm, and then we choose the largest one as the first, as the LK, as the first index, and then we do the projection to LK, so we get P CLK ZK, and then we do the similar process. We calculate the distance and choose the largest one as the second index RK. So we have two indexed here, LK and RK, determined by the maximum of the distance. So this is called the most violated constraints. And then if we assume the site is in form of function inequalities, we can have most violated constraints in function value variance. So it is similar, but here we just calculate the function value at each point, which will be much cheaper than the distance. Because here, if you want to calculate the distance, which means you need to calculate the projection first, which is already an optimization problem. It takes a lot of resource to solve. But here, calculate the function value in many cases would be much cheaper than calculate the projections. So we calculate the value of the projections, and then we choose the maximum one as LK. Then we do the projection and calculate all the values at this projection point. Then we choose the largest one as the second index, which means the RK. So this is most violated constraints, but in function value variant. Okay, so in our first paper, we proved the convergence with both almost cyclic, most violated constraints in distance variant and in function value variant, and also the convergence rate. Okay, so next part is a convergence result. Okay, first I want to introduce some basic tools for the convergence result. Actually, as far as I know, there are two ways to prove the convergence result, the convergence of the sequence. One is use the Fisher monotonicity and its corresponding result. It's here. So what is a Fisher monotone sequence? Fisher monotone means the sequence will get closer and closer to any point S in the set M. Okay, so if we can prove a sequence is Fisher monotone with respect to some set M, then first we can get it's bounded. Second, we can get the distance sequence converged. And the third is what I said, corresponding theory. It says if we can prove there exists a clustered point X star of the sequence, and then this clustered point belongs to the set M, then we can prove the whole sequence converges to the X star. So we have to prove two ways. We have to prove 2 points. First, the sequence is Fisher monotone, and the second is that we prove the there is a cluster point, and this cluster point belongs to the intersection of the M site, which then we can accomplish the proof. Actually, there is another way, which is not very popular, I think, but it has been used to prove the Douglas-Hartford method for the feasibility problem, which is first we prove the operator is firmly non-expansiveness, and then we can get the fixed point iteration will converge. and then we prove the fixed point side is equals to the solution side. Then we can finish the proof. So there are two ways, but here we use the first way. We use the phasor monotonicity. But actually, I think we can also use the second way, which related with the firmly non-expansiveness and the fixed point iteration for the SCRM or CRM, which is also possible. Okay, so first result is from the previous paper, Roger's paper in 2020, which means the CCRM operator with respect to set A and B has the property of firmly quasi-non-expansiveness. Actually, from this, we can very easily get that the operator we define here with respect to set Ci and Cj also have this property, because the intersection of M set also belongs to the intersection of any Ci intersect with Cj. So we get this property very easily from the previous one, and then we can get the sequence is phasor monotone. Just eliminate this term. So the sequence is phasor monotone with C, the intersection of all sides, and then we can also get the distance between zk plus 1 minus zk approaches 0, which is quite important to our result. And then we can also prove this result. Actually, in each step of our algorithms, it preserves the phasor monotonicity, which means no matter what you did, the centralized process of the simultaneous circumcenter, the point will never get further from the intersection. Which means it will get closer and closer into intersection. So this property, the fourth property, gets from that the phasor monotonicity of the whole sequence. Okay, so in the following slide, we call SCRM with almost cyclic control sequence is algorithm 1, and algorithm 2 is the SCRM with the most evaluated constraints, but in distance version, and algorithm 3 is the most evaluated constraints in function value version. First, we got the convergence for algorithm 1. Okay, I just say a little bit about the idea of the proof. First, we proved the sequence is phasor monotone with respect to intersection, but obviously we already get here. We already get it from this phasor monotonicity corollary. Okay, so because it's phasor monotonicity, so the sequence is bounded, so we can assume there is a subsequence converges to the point Z star, and what left is we just need to prove this Z star belongs to the intersection. That's enough. So because of the definition of almost cyclic control sequence, we can always assume that there is another sequence Kj less than Hj and less than Kj plus Q. Q is the number related with almost cyclic, and then we can such that this LHJ equals to Q. Q is any number from 1 to M. And then by the triangular inequality, we can prove that when J approaches 0, ZHJ minus ZKJ equals to 0. So, so we can conclude that this Z star belongs to CQ, because this Q is from 1 to M, so we can assume that this Z star belongs to CQ, and then we can, because this Q is any arbitrary integral from 1 to M, so that we can conclude that this star belongs to C, which is intersection. And then we can get the convergence of the second algorithm, which means the most evaluated constraints with most evaluated constraints. And the idea is a similar. First, we get the phasor monotone, which is already there, and then because of boundedness, we get a subsequence convergence to this star. and the left is to prove the clustered point belongs to the intersection. So first we use the definition of the most evaluated constraints. So we get the first inequality, and then we use the definition of the distance, and then we use a property I mentioned before, the feature monotonicity of the whole sequence. So we get this inequality, and then we take J approaches in infinite, so we can see that this star, distance of this star, and the set CI is less than 0. And for each I from 1 to M, so we conclude that this star belongs to the intersection. So this is a convergence of the second algorithm. And the third one is a most evaluated constraints for the function value version. So it's the same, but different here, we use the local ellipsis continuous of the convex function. We use this here, and we also get a similar proof. Then we get the result. Okay, so next I will talk a little bit about the convergence rate. We get two kinds of convergence rate. First, linear, and then superlinear. Unfortunately, for the almost cyclic control sequence, we didn't get the linear one. But recently, I have think about that, because recently I'm doing something about the stochastic control sequence about the CRM. Yeah, I think maybe we missed something. I mean, we can do something more. We can prove the linear rate for the almost control sequence. Okay, so before prove the convergence rate, we have some assumptions about the error bound. First is the error bound for two sides. For the two sides, so it's a standard definition. But here we have M side, so we need the some omega multiplies the distance they say is less than the maximum of Z to the array side CI. So this is, we call it EB1 here. And we also need EB2 because we have the algorithm for the function value version. If the site is in form of the function inequality, we assume this arrow bound EB2. Here we just use the function value instead of the distance, but we also have this maximum here. Actually, we have the relationship between EB2 and EB1. Actually, we can prove that EB2 is stronger than the EB1. As long as you have EB2, you can use some properties and prove that you can also get the EB1. Okay, so first result is about the distance sequence of the algorithms 2, which is most evaluated constraints but in distance version. We can prove the distance sequence converges linearly with a constant beta. Beta is equals to the square root of 1 minus the omega square. And then together with a property about the feature monotone sequence, which says if the distance sequence of feature monotone, if xk is feature monotone and the distance converges linearly, then the whole sequence converges linearly. Okay, so together with this property, we can get the algorithm 2 convergence linearly to some point in the intersection. And this is what I said, the relationship between EB1 and EB2. We assume the EB2 holds, then we can get the EB1, but with a different coefficient here. Okay, so also we have with this lemma, we can get the superlinear rate also for the algorithm 3. Which means the most evaluated constraints in the function value version. We can get the linear convergence rate. So then I just want to introduce the superlinear rate about the algorithm 2. Actually, this property of the superlinear convergence comes from the CCRM, which means the centralized circumcenter reflection method. I think which is a highlight of the CCRM. As far as I know, up to now, for the convex feasibility problem, both sequential and simultaneous method and also Douglas-Hartford method, they cannot have the superlinear rate. Only the CCRM and also here the SCCRM with most violated constraints can have the superlinear rate. Okay, so but here we also assume some additional hypotheses. Here we also assume the interior of C is non-empty, and also the boundaries of Ci is differentiable manifold, which in some sense means that the boundary is smooth. But it is not very strict assumptions. Then we can first get the distance sequence converged superlinearly. Okay, so with another property of the feature monotone sequence, it says if the sequence is feature monotone and if the distance converges superlinearly, then the sequence converges superlinearly. Okay, with the previous assumption, the boundaries is differentiable manifold, which means smooth boundaries, and with this property of feature monotone sequence, we can prove our algorithm 2 and algorithm 3 with most violated constraints, both versions convergence superlinearly. This is the convergence rate about our algorithms. Okay, next is about the numerical results. So we test the algorithms 1 and algorithm 3. Here we didn't test algorithm 2 because we regarded the algorithm 2 is not very practical, because in each iteration you need to, yeah. In another way, I want to say the algorithm 3 is much practical or much cheaper than the algorithm 2, because you just need to calculate the function value at point xk and choose the largest one, and then you can do the iteration. And also we compared with the CRM in product space and the sequential projection method. We test our problems to the to several ellipsoids. Ellipsoids is formulated in this way, and but here I need to say that there is problem of the project to the ellipsoid. Actually, although ellipsoid is a very classical convex and closed site, sorry, here should be the ellipsoid and its interior. It's a very classical convex and closed site, but we do not have closed formula to calculate the projection to the ellipsoid. So we use the ADMM to calculate the projection from any point to the ellipsoid. Okay, so we have the result here. We can say here the algorithm 3 with the most valid constraints performs much better than all other algorithms. Here I need to say thank you to Professor Louis Hafel. This numerical result comes from the work comes from our paper, but the Professor Louis Hafel made the main contribution to the numerical experiments. Okay, so this is about the successive centralized circumcenter reflection method. Actually, I just want to say a little about what I'm doing now. Actually, I'm doing the CRM with a stochastic control sequence. First, we choose the pair LK and RK randomly from 1 to n with some distributions here, but I just used the uniform distributions, which is simple one. And then I got the sequence, the random sequence xk is stochastic feature monotone with respect to C. Then we can prove that the sequence converges almost surely to some random point in the intersection. And then I can prove here we cannot prove the distance sequence is linearly, but we can prove the distance sequence with expectation convergence linearly and also superlinearly. But for the numerical experiment, I didn't do it yet, but we didn't expect too much, because I expect that the behavior of the stochastic control sequence is somehow like the almost cyclic or cyclic control sequence, maybe a little better, but not too much better. Yeah, but it's another kind of sequence. Maybe could have another very nice background. Okay, so here is a reference. First is the original paper of the circumcenter, and the second one is the centralized CCRM, and third one is our SCCRM. Okay, thank you everyone. Thank you for this. That's all.
Obrigado, Odilio.
Okay.
Alguém tem perguntas? Pode falar, Mário.
Okay, thank you for your talk. Very nice. I think that for me it's just surprising that you obtained the superlinear convergence results. Okay.
Yeah.
Very nice. But I read this paper of Nick Wood many years ago, and after the paper of Nick Wood, there was a second paper that William Hager published in the same journal. By Herman, Sensor, and Kelvin, and these people that work with projections and so on. And they showed that in applications, projection methods were quite effective. I mean, especially in problems of tomography and things like that. And so there was this divergence between the results of Nick Gould and the ones of the other people. And in fact, I think that both were right in the sense that the examples that Nick Gould tested were the classical examples, say, of the cube collection type. I mean, the classical examples that you use that when you test augmented Lagrangians or interior point methods and things like that.
Okay.
And he showed that, well, in these examples, in fact, the classical method were more effective than projection ones. However, the Herman and Sensor and all these people said no, but in the applications, the projection methods are very effective. And I think the reason is that in the applications, the number of iterations that you expect from projection methods is not that big. I mean, but you are very happy frequently with 4 iterations or 5 iterations, 10 iterations, so on. So the kind of problems in which projection methods were very effective were of this class, that, well, the first iterations were enough from the practical point of view. So, well, and this is my question. Did you address this question in your method? I mean, is it possible that in your method, the objection of Nick Gould, I mean, the use of the projections, your projections, circumvention, and so on method, could be competitive with the classical approach of augmented Lagrangian, Newton, interior point, and so on? On the other hand, did you consider the effect of making only a few iterations of your method in terms of getting something good? I mean, the effect of the first iteration of your method.
Okay, the first, I have never compared with this classical method. I need to say I have never have this idea to compare with the Lagrange or some other method, but I will do that because we just compared with the projection-based method, like the not Douglas Hartford, the sequential or the simultaneous projections method, because we do not have so many, I mean, methods in this feasibility problem, only the classical one. And for the second problem, Professor, can you repeat a little bit again? For your second problem question, can you repeat a little bit? Hello?
My question is if you analyze which is the performance of your method in comparison their competitive the competitors one, just regarding the first iteration, not the asymptotic the asymptotic result. I mean, because I think that the few first iterations are crucial for the practical application of this kind of methods.
Yeah, I totally agree with you, because from the numerical result, we have seen that both CCRM and also our SCRM with most evaluated constraints converges very fast. For some problem, it converts like 1 or 2 iterations. It is very surprised, but it is a result. And for some other algorithms, it converts like less than 20 or maybe less than 10 iterations. It is very efficient in the first few steps. But also for some problems, it converts very slowly. But we didn't analyze very carefully about these examples which converges slowly. But for many examples, I didn't know the percent, but I want to say there are many examples it converges very fast. And on the other hand, the classical ones like the sequential simultaneous projection method converges, like linearly, I cannot say very slowly, but with many iterations. But indeed, our method and also the CCRM, original CCRM, converts very fast for many examples. This is what I want to say. Thank you very much for your question and advice, Professor.
Okay, thank you. Thank you. I repeat that I am really impressed because you obtained superlinear convergence in this kind of method. I didn't expect that this could be possible.
I'm also, when I read the original paper by Roger Bailing and Luis Rafael and Alfredo, I was also surprised. I cannot believe it, because we just use projections, because as far as we know, we cannot get superlinear rate with only using the projections. But here in the Circum Center, they just solve a linear system with 2 variables, but which is very, very cheap compared with the projections. So we can say it a kind of projection method, but with superlinear rate.
Okay. Thank you.
Thank you, Professor.
Well, I had some questions and my 2 cents on the comments of Mario. Hello, Dilio. How are you? Hello,
fine. Hi, fine. Yeah, nice to see you.
Well, I'll begin giving my 2 cents on what Mario asked and what Dilio answered. We have a paper where we compared with the ART. ART is the sensor method, right? And Mario is correct, because on many applications, you don't need like a very, very high accurate solution. You are pleased with an accuracy of, like, I don't know, 10 to the minus 3 or something like that. So those suitable for these, because they can achieve this lower accuracy very fast, and then they start to zigzag or something like that. Now, CCRM and all the circumcenter type methods, they have this Newton type flavor, so they accelerate the so-called projection type methods in a way that they go towards the solution much faster, like Newton does. So when you are close, and we were able to prove this, the superlinear convergence is what Newton gives, right? When you are close to the solution, and given some regularity, we proved the superlinear convergence, which was a rather interesting result, of course. But just we knew by the experiments that this is what was happening, because we were always very, very fast. But so that's what happened, and we compared with the ART and the CERT, and I remember reading this Nick Good paper, and then the answer by Sensor and others, and it's very, very interesting. And so Mario remembering this answer from Sensor is very, very nice. So my question to Dilio is regarding the last part of your presentation because it's new to us, and we talked a little bit by using chat, but I never saw. And do you think that in expectation you will recover the linear or backslash superlinear result, but in expectation, of course. But what do you think will happen on the practical side? Because when one is using stochastic type projection methods, they tend to be much faster than regularly one, or like the cyclic one, and nobody knows yet why. So what's your expectation regarding the numerical side of the so-called, how you said, randomized circumcenter method?
Okay, yeah. I will answer your question later. First, I want to say that I just talked with Alfredo before, so Alfredo, I want to say hello to everyone here. And actually, my answers come from Professor Alfredo. Yeah, not all of them, but part of them. Actually, the behavior, we can imagine the behavior of for common examples, not for yield examples. We can imagine if we choose randomly, the behavior of the algorithms will be somehow like the behavior of cyclic, yeah, because if you use the uniform distribution, so we can imagine it would be not as fast as most violated one for the common examples, not for yield examples. And in this sense, actually, to be honest, even if I did it, I want to write a paper about that, but I need to say, up to now, we do not have a very strong reason to use the stochastic control sequence, because I can ask, why didn't you choose to use most violated constraints? It performs very, very nice, but maybe we can analyze some examples we used before, because we have some examples that CCRM works very well, of course, works better than other algorithms, but it cannot convert in very few steps, just as the professor said. We have some examples, a few examples that the CRM or the SCRM cannot convert so fast in just in less than 10 or less than 20 examples. I mean, maybe this examples is yield examples, or we can find some other yield examples or large. I don't know whether it exists, but if the number of the closed site is very large, we have more than 1,000 closed site, maybe in this sense, the randomly would be useful, because if you just calculate the distance to 1,000 or maybe 5,000 site, the distance would be very, very expensive. So maybe in this sense, the random control sequence would be useful. That's all. That's my answer.
Yeah, I would say that's the main reason for using, because all other projection type methods using, for instance, for solving, I don't know, linear inequalities, okay? You can use this to solve linear inequalities in a sense. And if the matrix is, I don't know, some kind of yield condition, you may have problem computing all this distance. So a randomized version will come at hand here to solve the problem, because everybody uses it and you have the circumcenter acceleration. So I guess this will be like the first thing that we should test this. Yeah.
Yeah.
Okay. Thank you, Dilio. Thank you.
Okay. Thank you.
Oh, go ahead. Say.
Okay.
Just saying that.
Anyway, except the uniform distribution, maybe we can develop some other distributions. I mean, with respect to the structure of the problem. If the problem has special structures, we can have different distributions. But up to now, I only use the uniform distribution. That's all.
Mais alguma pergunta, comentários? So thank you, Dilio. E a gente se vê no próximo seminário.
Okay. Thank you for your invitation. Thank you, everybody here.
Congratulations.
Okay. Ciao, ciao.
Tchau.